Hi, in this video, we will talk about the superposition principle. In electrostatics, we have electric forces wherein objects or particles exert an electric force to other particles, charged particles, and sometimes there are more than two particles that are interacting with each other. And with that, there might be more than one electrical force exerted on a particle. Now, the superposition principle states that each charge will exert a force on another charge so as if no other charges are present. The total force that a particular charge experiences due to a collection of charges is the vector sum of all of the individual forces. So all of the particles that are present around a point charge or around a specific particle that we are looking into, they will be the resultant vector of all of those forces will be taken as the net force acting on that particle. So what do we mean by that? So we look into is let's look into this illustration. You have three particles, Q1, Q2, and Q3. The net force acting on particle 1 is due to the forces exerted by Q2 and Q3, which is the vector sum of force 3 on 1 and force 2 on 1. So again, going back to the description of superposition principle, particle 2 or this charge 2, Q2, will exert the electric force on Q1 as if Q3 is not there. And Q3 will also exert its force to Q1 as if Q2 is not there. And because of that, Q1 will experience both of the forces exerted by Q2 and Q3. So let's look into a sample problem. 3-point charges are located along the x-axis. So there are three charges, Q1, Q2, and Q3, all in the x-axis. Point Q1 is positive 3.5 times 10 raised to negative 6 coulombs at position 0. Point charge Q2 is positive 8.5 times 10 raised to negative 6 coulombs at 2 meters from the point of origin. And point charge Q3 is negative 5 times 10 raised to negative 6 coulombs at 3 meters from the point of origin or point of reference, which is your Q1. So let's solve for the resultant electric force acting on Q1. So what's the resultant force acting on Q1? And there are two particles exerting electric force on Q1. Q2 exerts a force to Q1 as well as Q3. And if we look into the charges of our particles, of our point charges, Q1 and Q2 are positive. Therefore, Q2 will exert a repulsive force to Q1, and Q3, since it's opposite to the charge of Q1, then it will exert an attractive force. So how do we go about our solution here? Of course, we need to identify our given values. You have Q1, which is positive 3.5 times 10 raised to negative 6 coulombs. You have your Q2, which is positive 8.5 times 10 raised to negative 6 coulombs. And Q3, that's negative 5 times 10 raised to negative 6 coulombs. Since our Q1 will be our point of reference or the interest for our resultant electric force or vector sum of the electric forces, we need to look into the distance between Q2 and Q1 and Q3 and Q1. So the distance of R2 on 1 is, as you can see in the illustration, it's 2 meters. And R3 on 1, it's 3 meters. First, we need to solve for the individual electrical forces or individual electric force exerted by Q2 on Q1 and Q3 on Q1. So we need to solve for two forces first. So solving for force of particle 2 on 1, we need our Coulomb's law, which is Fe is equal to K times Q1, Q2 over R. So if we substitute our values, force 2 on 1 is equal to Coulomb's constant, that's 9 times 10 raised to 9 Newton meter squared per Coulomb squared, multiplied by the sum of our charges, or product of our charges, I mean. The product of Q1 and Q2, that's positive 3.5 times 10 raised to negative 6 coulombs, multiplied by positive 8.5 times 10 raised to negative 6 coulombs. There. Over the distance between them squared. If you input that in your calculators, you will get 0.0669 Newton. So that's the force exerted by Q2 on Q1. Now, the next force that we need to solve for is the force exerted by particle 3 on particle 1. We still follow the Coulomb's law, so we have 9 times 10 raised to 9 Newton meter squared per Coulomb squared, multiplied by the product of the charges, so we still have positive 3.5 times 10 raised to negative 6, and the other charge is negative 5 times 10 raised to negative 6 coulombs over 3 meters, since the distance between particle 1 and 3 is 3 meters. So the force of 3 or particle 3 on particle 1 is 0.0175 newtons. So these are our two forces acting on particle 1. Now we need to factor in what kind of electrical force is exerted by the particles Q2 and Q3 on Q1 respectively, whether it's an attractive force or repulsive force, because it will affect our answer. So again, Q2, since it has the same charge with Q1, it will exert a repulsive force, while your Q3 exerts an attractive force to Q1 since they are negative. So to solve for our resultant force, if we have here particle 1, so if we have particle 1, the positive, particle 1, since particle 1 is positive, again Q2 will exert a force towards this direction since it will repel it. So this is force 2 on 1, while on the other hand, your force 3 on 1 will be going towards the opposite side. As we can see here, this is repulsive and this will be attractive force. Now, if we focus on the forces acting on Q1 and we assume or we assign that F2 on 1 is directed to the left and F3 on 1 is directed to the right, then we can assign this as negative direction and positive direction. So if that's the case, so our F net, or our total force, the vector sum of the forces acting on Q1, so F2 on 1 is negative 0.0669 newtons, plus F3 on 1, since we consider it as positive direction, that's positive 0.0175 newtons, which will give us a net force of 0.0494 or negative 0.0494 newtons, or you can also write it as 0.0494 newtons directed to the left. So this is now the resultant force that is experienced by particle 1. Another sample problem. So we have here 3 identical point charges with charge Q is equal to positive 3 times 10 raised to negative 6 coulombs are placed at each vertex of an equilateral triangle ABC as shown in the illustration. So if the side of the equilateral triangle is 0.01 meters, find the resultant electric force at vertex A. So we need to solve for the force exerted at vertex A, which is your particle QA. Now, it's mentioned here, we have here in our problem that it's an equilateral triangle. So we should remember that an equilateral triangle, it has the same length on all sides and it also has the same angle for all of its vertices. So we must remember that. And since it is an equilateral triangle, so we know that each of the interior angle will be 60 degrees. So what are our given values? Since they are identical, your QA will be equal to your QB and also equal to your QC, which are all positive 3 times 10 raised to negative 6 coulombs. Now, if we look at it, since all of them are positive, this is positive, this is also positive, and this is also positive, then therefore, if we are to solve for the force exerted on QA, QB will exert a repulsive force on QA, as well as QC will also exert a repulsive force on QA, since they are both positive. So this will be the force of C on A and force of B on A. Now, another given value here is the distance between your charges, since the triangle is equilateral. So this side of 0.01 meter will be the same or be equal for both the distances between QB and QA and QC and QA. So R1 or R in general is 0.01 meters. So it's the same for all of our particles. To solve for the individual forces, so you have force B on A and force C on A, we need again to use, of course, your Coulomb's law to solve for the electric force. So let's write it here so that we will not forget. Now, let's solve for the first one, QB on QA. So force B on A. Since QA and QB again are like signs, they will create a force of repulsion. So force B on A is equal to your Coulomb's law, 9 times 10 raised to 9 Newton meters squared per Coulomb squared, times you have positive 3 times 10 raised to negative 6 coulombs. We square it since your charges are identical. You can just proceed with squaring the value over 0.01 meters squared. So that's cancelled out. So the force exerted by particle B on A, or point charge B on A, is 810 newtons. Now, for C on A, we have force C on A, still following the Coulomb's law. So we have 9 times 10 raised to 9 Newton meters squared per Coulomb squared, multiplied by positive 3 times 10 raised to negative 6 coulombs. We square it since, again, they are the same. They have the same value, 0.01 meters squared. And if you look at it, it's also the same on the values in F, or force B on A. Therefore, FC on A is also 810 newtons. So point charge B again repels point charge A. Thus, we have here the force directed right up at 60 degrees with the positive axis, which is also the same with the force exerted by QC on QA. So again, thus, FC on A is directed upward to the left at an angle 60 degrees with the negative axis. As shown here, if we draw it, so this will be the force experienced by particle A. So this will be 60 degrees, and this is also 60 degrees. So we need to solve for the resultant force. If you remember if you have watched our video on our lesson on vectors, especially in your lessons in Newton's laws, you were able to work with vectors. So we can place it in a table. So you have force B on A and force C on A. And you have your horizontal component and you have your vertical components. So you can place it like that. What will be the horizontal component of force B on A? Now, since this is positive 810 newtons, and you have here, it's when we look at it as placed in a Cartesian coordinate plane, your x-axis is in the positive side. Therefore, you have positive 810 newtons cosine 60 degrees, since the angle between the x-axis and the force vector is 60 degrees. Then we get a value of positive 405 newtons. Now for Fy, since it's in quadrant 1 again, or since it is in quadrant 1, then y is also positive. So you have positive 810 newtons cosine 60 degrees, or I mean sine 60 degrees, since it's already for the y component. This is now positive 702 newtons. So that's for force B on A. For force C on A, if we look at it, your x component for force C on A is on quadrant 2. Therefore, it's negative 810 newtons cosine 60 degrees. And that is negative 405 newtons. And for the y component, so that's in the positive y-axis, so that's positive 810 newtons sine 60 degrees. Oops, sine 60 degrees. And that's positive 702 newtons. So if we solve for the sum of the forces on x, that's 0, positive 405 newtons plus negative 405, and the sum of the forces along y, then we have 1,404 newtons positive. Now, when we solve for the resultant force here, if you remember how to solve for the resultant force out of the components, so that will be F is equal to the square root of the sum of Fx squared plus the sum of Fy squared. And since in this case, Fx is 0, and we can cancel out this expression, the square and the square root, therefore force, or the net force, is equal to the sum of the forces along y. So therefore, force is equal to positive 1,404 newtons. Or, to be correct, to be precise, that's 1,404 newtons upward. So this will be our resultant force that is experienced by particle QA as QB and QC exerts a force on it. So that's for superposition principle. Again, in superposition principle, it states that a force or a point charge that exerts a force on another point charge will exert its force as if there are no other charges present. And the total force that's experienced by a point charge is the vector sum of all of the electric forces exerted to it by the other charges that interacts with that charge. So that's superposition principle. So thank you very much for watching this video.